Hello everyone, welcome to this online talk on physics of language models, part 2.2, how to learn from mistakes on grade school math problems. So if you came here from my ICML 2024 tutorial, in that tutorial I covered a 20-minute section of this talk, but only covering the very high-level results and overviews. So today I'm going to delve into more details. So the motivation here is that even nowadays, even the strongest LLMs still make reasoning mistakes. So for instance, you can give it a problem like this. So you're talking about a bunch of different boxes. Each box has its own weight, and it may also contain some other box inside it. And then you can ask, for instance, GPT-4o, what is the total weight of box X? So it's going to do some calculations, and if you give up GPT-4o like a problem that's only of like say 4 lines of difficulty, then it probably will always succeed. But if you give it like a problem of 6 lines of difficulty, it may start to fail. If you give it like a 10 lines of difficulty of a problem, then it almost always fails, and so on. So here, like the typical mistake is to maybe compute the weight of something incorrectly by basically missing another box that has clearly been stated in the problem statement, but the model just didn't realize it should include that, and therefore it makes a mistake. So this type of mistake is very common. You can very easily reproduce this like on GPT-4o and the other large models. So how to improve on this? So the most natural thing to do is to continue to ask the model to, say, go over the problem statement and by sentence, and to verify your line 1. So then GPT-4o is very happy to do that, but it realizes maybe something, but in the end it still like insists that it's not making any mistake. So if you continue to force the model to verify and say, verify this is not correct. So eventually it's very likely going to make the correction and correct it. But in this way of correcting this self, we see at least 2 issues. One is that it's like even with the strongest modern LLMs, they're still very bad at correcting their own mistakes. So in fact, this example above is just one of the very rare cases that the model can correct such mistakes. So for instance, we tried many things like please verify and correct your solution. And we tried like check your solution line by line carefully, matching it to the problem description, or maybe you made a mistake in line 1, please correct it, or even like I'm very sure you made a mistake in line 1, please correct it by checking blah blah blah. So in all of those cases, actually the model fails to correct itself. So the example above was one of the very few examples that we actually enabled the model to correct itself. So therefore, like, one issue with this type of like multi-round kind of prompting approach to let the model correct themselves is that the accuracy is not very reliable. But this is not the topic I'm going to cover today. So the topic I'm going to cover today is another issue, actually an orthogonal issue. That is, suppose the model, maybe tomorrow's model, right, can correct itself via like multi-round prompting. Then if the model can correct that, then why doesn't it correct the mistake immediately after a mistake is made? So instead of like really like prompting the model, run after run to correct something, this is very inefficient. So suppose the model, can, after making a mistake, immediately correct it. So then it can avoid generating, all the follow-up like tokens that are useless because they were built like upon like an incorrect sentence. So therefore, like if it can correct a mistake immediately after it's made, that will be much more efficient, and also you can speed up the inference. So this is actually the topic I'm going to cover today. That is, I want to delve into the possibilities of making a model to correct itself immediately after the mistake without multi-round prompting. So how to achieve this? The simplest idea, I would say, is to maybe train an error detector model to catch the mistake. And then whenever you catch a mistake, then try to regenerate, say, from the previous sentence and so on. So let us first see like how this idea works. So this idea has 2 parts, catching a mistake and regenerate. So let me go over them one by one. So how to study the scenario in which the model catches mistake, right? I need to prepare a data set to begin with. So this is the data set that we use, and we actually use this one from our prior work. So you don't need to read all the details here, but basically, like, it's a math data set that tries its best to simulate GSMAK by like enhancing the reasoning difficulty, but removing the arithmetic difficulty and so on. So basically, in this data set, each sentence describes a parameter, saying that a parameter maybe depends on 5 times the sum of another 2 parameters. So therefore, the problem statement is sentence after sentence describing basically a dependency graph. And then a solution with respect to each problem is just a computational transcript that says, you know, for this parameter, maybe it's already like given in the problem statement. The next parameter maybe it's already given. The third parameter, it's the multiplication of 7 times another one, and it starts to compute like this. So that's how that's a data set that we created from the prior work. So what made this data set like particularly interesting is because on one hand, like, it's fully controllable, so we can control the data set. We know exactly like you know, what sentence and which step is incorrect and so on. So then we can very easily like we can very easily like check, you know, if a model fails on this data set, like why does it fail? And also very importantly, this data set is nice enough that it's self-contained, so you can pre-train a model directly on this data set to see how it behaves and so on. So now, like, an interesting thing from the data set is that once you pre-train on this data set, you can see that whenever the model makes mistake, it's typically of the same reason. That is, it tries to compute a quantity that is not yet ready for computation. So it defines the parameter as whatever parameter it tries to compute, but then it realizes, oh, like, I can't compute it, and therefore it starts to hallucinate. So we see this issue not only with models pre-trained that are directly pre-trained on this data set, we even see this same type of mistake happening a lot of times with GPT-4 and 4.0. So it also makes mistakes of this format. So therefore, like, we think this is a very nice starting point for us to study, you know, the mistakes, the reasoning mistakes of language models, and then let us study like how we can, how the model can correct mistakes whenever it makes a mistake of this type of format. So the very first thing we did on this data set is to do probing. That is to check if the model from its internal states, to check if the model already knows it has made a mistake after, you know, defining the parameter. So actually, our solution of this data set has a particular format. That is, each solution step begins with defining a parameter, and then it starts the computation. And if this parameter is not ready for computation, then in principle, at this position, the model can already know that. And in fact, we discovered that the internal states of the model indeed exhibit a regretful pattern. So that means after spelling out the mistaken parameter, the model already knows it, that this is a mistake, and therefore it really has some regretful pattern. So this is actually a very precise statement, although it looks vague, but there's a like very comprehensive experiment behind this. That is, we can do probing to look at the internal state of the model to see that if the model at this precise position, whether or not it has already known that a mistake is made. So this is a technique that we introduced in part 2.1, but here, like, to make the paper a bit self-contained, let me briefly mention what it is. So the idea over there is that we first pre-train a model on this math data set, and we freeze all of the weights. And then whenever you are given a problem, you let the model generate its own solution, right? And now you feed its own solution as input to the model. You feed it again. And this time, like, you start with a problem, a question, and then the model's own generated solution. But then the important thing is that at each solution sentence, right, after stating the parameter, then at exactly this position, this English word as, at this position, you forward the model to the very last layer, and then try to perform a binary classification task. That is to detect if, to predict if this sentence has a mistake. Okay, so we freeze the entire pre-trained network, and the main idea here is that you're trying a linear layer on the output, and also you make a tiny low rank update on the input layer, so you freeze the entire network by changing only the input and the output layer to perform this new task of binary classification to detect if the model knows a mistake. And our main idea from the prior work is that because there are so few like trainable parameters on this new task, so therefore if the binary classification has a high accuracy, then it pretty much mostly comes from the pre-trained weights of the language model. So therefore, if the accuracy is high, then we say that the model already knows, this sentence has a mistake, and so on. So that was the main concept of the prior work. And then we use that to actually discover that when the model makes a mistake, actually there's a probability between 50% and 70% that the model actually knows it has made a mistake. Okay, so that was like the precise statement of what this means. And if you think about it, this may sound weird. That is, if the model already knows it has made a mistake, why does it say it to begin with? So there's actually a very simple explanation. That is, before the model spells out, this parameter in this new step, then the model needs to, internally think, among all the parameters, what you want to compute next and so on. But after stating it out, the model transits to a new stage. That is, it needs to now compute this parameter. So therefore, it sees maybe this parameter depends on A, B, C, but maybe A and C are ready, but B is not yet ready. So that was actually the moment that the model uses its attention mechanism to kind of figure out, no, I have made a mistake. So this is why, before the model says this sentence and after it says the sentence, the internal states may have very different patterns and so on. So therefore, the model actually regrets for the mistake it has made. So this is the first result that we discovered. It's essentially just using prior work, so that's why we call it result 0. But there's already some very important conclusion to be made here. That is, error detection is easy. So you can essentially just pre-train a language model on error-free data, and its internal states can already tell you if you had made a mistake. So a pre-trained model on error-free data is almost already an error detector. You can just change its input layer, output layer just a tiny bit to make it an error detector. And not to say that you can also use lower fine-tuning very easily for error detection and so on. So people study this a lot, fine-tuning a model for error detection. So this is easy. So that's the first point of this work. And now, suppose you can detect error, right? How do you correct that? As I said, the very simple idea is that how about whenever you detect an error, then let's try to go back to the end of the previous sentence and regenerate. So this is what we call retry upon regret. Okay, so on this data set that we created, if you do this technique of going back to retry, then what's the accuracy gain? So we discovered that it indeed improves the accuracy by about 2% on this data set, and especially if you compare that to a beam search, if you do beam search, the accuracy improvement is almost none. But if you do this idea of retry upon regret, that is to backspace whenever the error is detected, then you can get some accuracy gain. So this is very easy that you can implement it, but you see a lot of downsides already from here. So number one, very importantly, is that the accuracy gain is very small on this data set. And there's actually a reason for this, because you're not really doing anything smart. You're just using randomness to retry. So this is not really error correction. So you're just doing error detection and then retrying using randomness. So you can imagine that this is not very smart, and that's why you don't get a big accuracy improvement. The second important thing here is that this really requires the error detector to be super accurate. So you don't want to have false positives, and you also don't want to have false negatives, because otherwise you may have infinite loop. Maybe you did not make a mistake, but error detector says you made a mistake. You go back to the previous sentence, but then the model may generate the same thing again, and so on. So you don't like this to happen. So therefore, you need the error detector to be very, very accurate. So in fact, this 2% gain comes from an error detector that was 99% accurate. So that's already super accurate, but it only gives you 2% improvement. And by the way, we also put a limit, that is we retry a maximum of 10 times. because if you don't put a limit, then maybe like the model just keep generating and so on. And in contrast, if you change the error detector to be 100% accurate, then you get a much larger accuracy gain, but that's really too ideal. So you see that this type of accuracy gain really relies on a very highly accurate error detector that may not be very ideal in practice. And finally, this type of retry technique still like has very high inference cost because although you're not having multi-round of prompting, but you still have to retry maybe a number of times, and you have to also keep track of an error detector model that's a second model comparing to your original model. So there are many downsides with this type of retry upon regret technique. So therefore, like the rest of the talk is going to study the following question: that is, can we have a single model? Maybe autoregressive and no regeneration and no multi-round prompting and so on. Can we have just a single model to achieve everything, to correct itself on its own? So this question is important because if eventually we want to really get close to AGI, right, then we just want one single model to handle everything, not only making mistakes, but also to correct mistakes on its own, just doing everything like automatically. So is that actually possible? So this is what we want to study in the rest of the talk. So our idea is the following. That is, we wish to study the possibility of introducing basically math data with retry. So it's of the following format. That is, we try to introduce mistakes followed by their immediate error corrections into the pretrained data and see if the model can actually learn to correct mistakes of this format. So the most intuitive example is the following. That is, we can create data such as like A implies B. Oh, I made a mistake. Actually, A implies C. Okay, so A implies B is maybe a mistake, and A implies C is the correction. So a mistake is immediately followed by their correction. And we want to see like how a model behaves if pre-trained on data of this format. So concretely, how to create data of this format. So in the synthetic setting of this data set, IGSM that we created from the prior work, because we have full control of the data, then we can introduce arrows like in any way we want, right? So we on the synthetic. So I'm going to tell you later in the talk that is how to maybe create such data in practice. But for now, think about it as using the synthetic data, and then we use the parameter p to control like how much error we want to have. So following like each correct computational step, we try to with probability p like add a wrong step and followed by a special token that we call back. Okay, so we prepare our data like this. So after each sentence, with probability p introducing one mistake, and with probability p squared introducing two mistakes, and the p cubed with three mistakes, and so on. So that's like a synthetic data that we can create. And suppose we pre-train a model on this type of data. We want to study, how things would behave. So a very important point here is that, this is just the data that you pre-train the model on. So there's no change to the autoregressive like training or inference procedure. Namely, like for instance, when generating a next step, the model actually sees all the mistakes in the past. So this is nice because, for instance, for the model to predict this token back, it actually needs to be able to detect error, right? It has seen like already this sentence, is already generated here, and then like to force the model to learn this special token back is actually asking the model to learn to detect error. So this we know the model can do that. So therefore, like we can introduce this also to the data. And more importantly, is that we are also providing data to teach the model to correct error. For instance, here, when the model is generating this sentence, it's actually conditioning on the past. That is, the model already sees that, oh, it has made two mistakes before, and conditioning on that, I don't compute these two parameters. Then what is the parameter I should compute, and let it compute and so on. So this way of creating the pre-trained data, we're in some sense combining the error detection and error correction altogether into a same autoregressive task. And therefore, like there's no change to the training procedure, right? And we want to see how this type of data could help the model to do reasoning. So although it sounds nice, but if you think about it, if this is the first time you see it, you may immediately have some question that does this work at all? In particular, by introducing a lot of mistakes of this format, then doesn't this actually encourage the model to make mistakes, right? Like the correct next solution step might be to compute this one, but by introducing mistake of this format, then doesn't this, force the model to actually learn to generate mistakes? That is like, for instance, to generate A implies B. And on top of this, do we need to do like label masking? That is to mask out the labels of the mistakes so that to encourage the model not to learn mistakes. So there are actually many subtleties that could arise from this question of this pre-training procedure. And this is like why like we did some very controlled experiments to study like how this works and what are the consequences if you do it in this way and so on. So we have actually 4 sub-results to show. The very first thing we discovered is that actually quite counterintuitively, that is within a reasonable range, that actually the higher P is, the better. So you had better have like more errors in your training data. That actually makes the accuracy go even higher. So if you don't have any error in the training data, that's the original like error-free data, then you have only maybe accuracy 78%. But if you start to have like 10% of the error, the accuracy is like 90. But if you start to have 50% of the error, so nearly like half of the solution sentences are mistake sentences, then you start to have even higher accuracies and so on. So I want to point out that this is actually a very controlled experiment and very fair experiment that we did. So throughout this talk, I'm going to show you maybe only some number, but what's behind the scene is actually a lot of numbers. So for instance, these 2 numbers just show up here and here, meaning that for one of the data sets that we tested, that for the hardest problem within that data set, then you see this huge improvement from basically 78 to 94.8% accuracy. But if you look at maybe a simpler problem, then you don't have that much of improvement. But there's a reason. That's because that problem already like has a very good accuracy. So therefore, like you don't expect too much improvement and so on. So I'm using this like single number to give you like a short abbreviation of actually what is behind the scene. That is inside the paper. You're going to see many more numbers in the table and so on. And also like I'm only showing you like one data set here, but we have at least 3 more data sets that will show you similar results. So the second remark I want to make is that whenever we do comparison in this paper, we're doing it in a very fair and strong manner. So for instance, we made sure that when you compare models, they were pre-trained using the same number of tokens. So let me point out why this is important. So whenever you talk about error-free data, right, is typically shorter because it doesn't include the errors. So therefore, like if you have error-free data of this, if you train like using the same number of tokens, you are actually making sure that, and if you pre-train using error-free data, then you see more math problems comparing to if you use retry data. And if you have like a smaller p, then you are actually seeing more problems comparing to like a larger p and so on. So therefore, like we are actually having a stronger comparison. So we are giving advantage to the model that is pre-trained using error-free data, yet it still like achieves a low accuracy. And we are giving a hard time for the model pre-trained using the retry data because it sees like fewer problems, although the same number of tokens, but the fewer number of problems, yet it still like achieves a higher accuracy. So in this way, like we made sure that our comparison is fair and actually more fair and very strong. And at the same time, we made sure that our models were pre-trained using the same hyperparameters, the same learning rate, weight decay, like the number of steps and the learning rate schedulers. And in particular, we even made sure that our learning rate and weight decay were best tuned for the error-free case when making this comparison. So therefore, this type of comparison, whenever you see like in today's talk, it's not only fair, but also very strong. So that was the first observation. So the next observation we made was back to the question I raised earlier, that is, suppose your pre-trained data has so many errors, then how about during the inference time? Does the model start to generate a lot of errors? So it turns out that no. So even if all the pre-trained data has a very large P, a very large number of errors, then during the test time, the model may almost never retry during test time. So here is a concrete table from the paper. That is, for instance, if you take P equals to 0.4, then even if you look at the hardest problem that we have tried, then although in the training set, such problems would have maybe at least more than like 10 mistakes and followed by their corrections in the data, but during the generation, during the testing time, the model just retry at most an average of only one time, for those even hardest problem that we have evaluated. And that's when P equals to 0.4, and if P is like smaller, then the number of retries during the test time is even lower. So only in the scenario when like P equals to 0.5, then we see that the models start to retry a lot. But still, like this average of like 3.7 number of times is still like much smaller than the number of retries the model makes in its pre-trained the number of retries the data makes in the pre-trained data. So why did this happen? So actually, the reason of this traces back to even our part 1 of this series of work, in which we studied language structures. In particular, we studied the grammars. And we discovered over there that is, if the pre-trained data contains a lot of, say, grammar errors, then during the test time, as long as you use small temperature or if you use beam search at inference time, then the model almost never make grammar mistakes. So if you haven't seen our work of part 1, let me give you maybe a very intuitive explanation here. That is, suppose the model has already maybe generated the first solution step, right? It's trying to generate the second solution step. Then if you use temperature 1, then the model will actually, with probability P, generate a mistake. So because it's trying to mimic what input distribution it has seen during the pre-trained data. But if you use a very small temperature, namely, for instance, if you use temperature equals to 0, then the model is encouraged to generate the most likely next solution sentence. And if, for instance, P equals to 0.4, then with probability 0.6, the model is encouraged to actually generate a correct solution step. And this is why, if you use a low temperature, the model may actually almost never retry during test time. And we discovered that even if P equals to 0.5, say that the true ground truth distribution have a 50-50 chance of using a correct step versus an incorrect step. But still, in that case, as long as the errors you introduce during the pre-trained data is sufficiently random, then, for instance, if there are maybe 2 possible correct steps versus 5 possible incorrect steps, then the model still has a higher chance of generating the correct step if you do the math properly. So therefore, even if your training data has a lot of error, as long as you use, say, a small temperature or some beam search with some large beam, like beam equals to 4, the model may not actually make frequent mistakes intentionally in the test time. It only tries to correct itself in the rare case where it makes mistakes, but it won't make a lot of mistakes. That's what I'm saying. So the next observation we made is regarding to also the question I asked earlier, that is, do we need to make label masking? So label masking, if you use PyTorch, just means to use this parameter called ignore index. That is, you try instead of having an autoregressive language modeling loss on all the tokens, you can try to exclude the cross entropy loss on those error tokens, right? So this is different from removing the mistakes from the data. Because, for instance, the model still needs to, the data still asks the model to predict, for instance, this token back. So when predicting the token back, the model still sees this mistake. And therefore, it's still using this data, even if you mask out all the mistake tokens, the model still learns to detect mistake. And for instance, in the next sentence, the model still is encouraged to learn to correct mistakes because the model still sees this as an input. It only so happened that these tokens do not contribute to the loss function, so therefore the model is not encouraged to make mistakes if you add label masking. So therefore, this is definitely a nice thing if you can add it. But what if you don't add it, right? And if you add it, for instance, how much accuracy gain can you additionally get? So we discovered something very surprising, that is, it's probably not really needed to add label masks. So only when in the extreme case, when p equals 2.5, we see that it marginally helps. So in our accuracy table, we actually discovered that, for instance, if you use p equals 2.1, then between with and without label masking, we did not actually see a much accuracy difference here. And here we also tried p equals to 0.2 and not much difference. Only in the case 1.5 we see a minor accuracy difference, but in fact, like it's better to see it just by counting actually the number of retries in a separate table. So we actually showed this in the paper. That is, in the case of p equals to 0.5, we see that without label masking, the model is making an average of, say, 3.7 number of retries per generated solution on this hardest problem. But once you add label masking, the model like makes fewer mistakes and it does like smaller number of retries as a result, and so on. So therefore, label masking works, it helps, but only marginally if you look at the final accuracy. So the last observation we made was regarding the model's capability of generating shortest solutions. So if you watched my talk on part 2.1, actually over there we mentioned that there is a very important property that the language models can achieve, that is to generate shortest solutions. So this is very non-trivial. It requires the model to do some pre-processing like topological sort to figure out what parameters are needed in the solution, what parameters are not needed. So now there's a natural question, that is, by introducing so many mistakes in this format, then does the model still preserve this skill of generating shortest solutions? So we discovered that actually, yes, adding retries, adding data like this format does not encourage the model to generate long and unnecessary reasoning chains. And for instance, if you don't have retries, then this is the number of average number of unnecessary computations the model does. But if you introduce retry, then the model, still generate the same average number of unnecessary computations. So therefore, like there's no much difference between like adding using retry data versus the original error-free data. So to conclude, we introduced this type of retry data, and we experimented it with our synthetic data sets introduced in the prior work by introducing errors followed by their emitted mistakes. And we studied like if this type of data is going to help the model to get higher reasoning accuracies. And a priori, as I mentioned, this like is not trivial, right? Because you're introducing a lot of errors, right? You're introducing errors and mistakes, and therefore, like, do they actually counterbalance each other? So is it actually better to introduce errors in this way? So what we discovered using very controlled experiments is that this not only works, it works actually in model excellent. It works super great. Like in fact, the higher like the probability is, the higher the amount of errors you introduce, at least within a reasonable range, then actually you get even better accuracy improvement. And also, like, even though you're introducing a lot of errors in the pre-trained data, it does not encourage the model to intentionally say mistakes in the inference time. So the model only in the very rare cases when it made mistakes, it tries to make corrections, but it doesn't like make the model to like just keep saying mistakes like all the time and so on. So we have this nice property. And also, like there's no need for label masking, so you don't need to mask out the errors during the pre-training. So you're not changing the training procedure. And finally, this is also not changing the model's reasoning behavior. So the model is still capable of generating like the shortest solutions. So these are very nice properties. So when combining them together, we see that it's very safe to include such metadata with a lot of errors and retries, and there's no change to the training or the inference procedure. So that's a very nice property to have. So this is about some positive results. So let me now go into some negative results. The first negative result we see is regarding beam search. So remember that we have this kind of error-free data and the retry data. And if you pre-train with the error-free data, I told you that you can get, for instance, accuracy 78%. And if you pre-train with retry data, you can get like 95%. But then how about beam search? Suppose you use like a very large beam, say beam like 32, that's much more than like what people use in practice, on top of this model A. And what's the accuracy? So we discovered that the accuracy gain is only like 1%, even if you use a very large beam. So this means that you can't really rely on beam search for correcting errors. And there's actually a reason for that. That's because beam search is still like, in some sense, using randomness to correct errors. So you really need, the retry data to teach the model to make error corrections. So this is like the first negative result we showed, that beam search does not give you a reasoning accuracy that's comparable to what you can get from pre-training with the retry data. So the next negative result, a very big one is regarding fine-tuning. So in practice, you may think about a procedure that is, after maybe pre-training a model with error-free data. Now, can we like fine-tune the model, say using lower fine-tuning with additional retry data to make the model perform like as well as pre-training with the retry data? Okay, so this is very desirable in practice, because in practice you may take some open source language models like, I don't know, Llama, Mixtra, and so on. Presumably, like maybe they were trained mostly using error-free math data, but without a lot of like retry data like this, right? And now suppose tomorrow you prepared some retry data, and you don't want to you want to recycle those models, right? You don't want to start from scratch. And now, is that possible to, for instance, fine-tune such a model, pre-trained using error-free data with the new additional retry data and to get some high accuracy? So we discovered that, yes, you can get some accuracy, but not really by much. So we actually did a very comprehensive experiment here by trying, even very large lower rank, and even adding like label masking, and with sufficient fine-tuning examples, even using like best tuned parameters. And the best accuracy gain we got was only 83%. And in most cases, the accuracy is actually even lower than the original model. So let me explain. In the case of p equals to 0.2, okay, that's the amount of errors we introduce in the data. Then we actually compiled with the original model that was trained on the error-free data, and remember that accuracy was about 78% accuracy. And now, if you additionally like fine-tune it using lower fine-tuning, even with like some very large rank, for instance, the QV rank is 256, comparing to the model size in which the hidden dimension is 768, so we were using GPT-2 small, then even if you introduce a super large model, almost comparable to the original QV matrix, and also you can do lower like fine-tuning also on the embedding matrix as well, you can do that. And even if like you introduce like label masking or not, you see that the resulting accuracies are not that significant, and in some cases it can even be smaller than the original model. So that was for like p equals 2.2, and especially in the case when you have a very small lower rank, like a rank 8 or 4, that's 8 in this case, you can see that the accuracy can even be smaller than the original model that's pre-trained on the error-free case. So that's for like p equals to 0.2, but we actually did a very, very comprehensive experiment in the paper. You can see it, in which, for instance, if you zoom in here, that talks about p equals to 0.5, and that was the only case that we discovered that the model can actually achieve a higher, the highest, like 83% accuracy. But that's a very rare case. So you require the model to have a very large lower rank, and also with label masking turned on, and also with retry rate being 0.05. So only in that case we got like 83% accuracy, but in most cases the accuracy is only like comparable and even worse than the original error model that's pre-trained using error-free data. So why does this happen? Okay, that's a very big negative result. So in fact, like if you compare this to full fine-tuning, you're going to see where this comes from. So we also did an experiment with full fine-tuning. and realized that the full fine-tuning actually works when there are sufficiently many of fine-tuned samples. Okay, so therefore it's not the fine-tuning that has a problem. It's actually the lower fine-tuning that causes this performance to be bad. So if you do full fine-tuning with like sufficiently number of fine-tuned samples, this is just continued pre-training. So therefore, like I'm not encouraging you to do that, but if you still want to do that, okay, let me show you what's the performance. So here is the full fine-tuning experiment that we did. So suppose that the model that was pre-trained on error-free data actually used T tokens. Then during the fine-tuning process, we continued fine-tuning the model with another like T tokens from the retry data. So this is why, like I said, it's almost just continued pre-training because we are, fine-tuning using the same number of tokens. So in this way, we see that the accuracy can be much higher comparing to the lower fine-tuning. That were like 85 until like 91% for p equals to 0.05 until like 0.5, for instance. And if you compare that with pre-training with retry data, say also T tokens, then you see that maybe in some cases it's worse, but in some cases this even looks better. So if you think about it, is this actually the time that we claim that full fine-tuning works better than pre-training? I claim no, because this is not a fair comparison, because in this full fine-tuning procedure, you're actually using a total of 2 T tokens from the data. So actually a fair and a stronger comparison would be with respect to like pre-training using 2 T tokens of the retry data. But if you do that comparison, you can see that the accuracy is actually much worse comparing to that. So therefore, like, yes, full fine-tuning works, but it works because it's in some sense just continued pre-training. So if you have fine-tuning, if you really want to do full fine-tuning, then you had better actually introduce such data at the pre-training stage and include that as early as possible. So this is our comparison to the full fine-tuning. So therefore, to conclude here, that is, unlike error detection, which is easy by probing or lower fine-tuning, as we saw like at the first result of today's talk, but error correction is actually a very, very different skill comparing to error-free reasoning. So it requires the model to have a very substantial weight change between like doing error-free reasoning and doing error correction. So this is potentially beyond what parameter-efficient fine-tuning can handle. That's why we think lower fine-tuning fails in this case, but full fine-tuning works. So therefore, like the lesson from here is that if you are capable of generating retry data of this format, you had better really include it as early as possible, even like during the pre-training stage, and do not wait until the fine-tuning stage, especially if it's lower fine-tuning or other type of parameter-efficient fine-tuning. So the final result I want to show you is regarding some preliminary progress towards how to really propel this type of retry data in real life. So here by retry data, remember that we mean errors followed by their immediate corrections. So in our synthetic setting, in the so-called IGSM data, it's very easy to create retry data because you have full control of the data. You know exactly what the solution looks like. You can introduce error like in any way you want. But in practice, there may be some procedure that can help us to create mistakes, errors, and the corrections without actually understanding the math problem, without understanding the solution, right? That would be more ideal. So we actually tested 2 ideas that we call a dumber idea and a smarter idea in this talk. In the dumber idea, the errors that we created are just some random sentence from the future. That is, you try to move some future, you try to copy some future sentence and move it to a previous step, and then followed by a back symbol. So this is not always a mistake because some of the solution steps are interchangeable in their order, but we still like try to introduce this kind of future step into an earlier stage and call it an error, followed by their original solution step, which was the correction to this error. So this is how we create the first type of mistake. It's very easy to obtain this in real life because you don't even need to understand the problem of the solution. You just divide divide the solution into steps, into sentences, and maybe copy like a future step into a previous stage and mark it as an arrow. That's one way to create retry data. Another way to create it, what we thought as a smarter idea, is to maybe introduce a random parameter from the problem statement and move it here to make it a fake mistake. So actually you can be a little smarter by choosing a random parameter in the problem that has not appeared in the solution and so on. So this we thought is smarter, and we also acknowledge that it's much harder to obtain this in real life because yes, you don't need to understand the solution, but you at least need to understand what are the possible parameters in the problem and so on. So you need to do a little bit parsing. So we thought this one would be better, but in fact, the dumber idea wins. So this idea actually gives you a higher accuracy gain comparing to if you use this smarter idea. So we actually thought about it. Why does this happen? Is that this type of data actually encourages the model not to skip steps. So therefore, like it could also be like very useful in practice to introduce maybe this type of fake mistakes. So to conclude here, that is, this is very preliminary progress regarding maybe how to create, how to prepare retry data in real life. So we're not saying that you should directly use this data we created for training future versions of LLMs. What we're saying is that because modern language models really struggle with self-correction, so maybe we should consider adding metadata with synthetic errors in some similar fashion of this format to as the new pre-trained data for the future versions of LLMs. So could that actually help? So in particular, one can try, for instance, prompting Llama 3, like some open source model, to introduce errors of this format. So the goal of this paper is to study, like, if you can achieve this, then what type of errors you want to introduce that can maybe give you a higher accuracy boost and so on. So this is like the goal of the paper, that is to study, like, suppose you can achieve this, then what is needed? For instance, then do you need to do label masking on the data, on the error? And our claim is that you probably don't need to, and you should introduce maybe as many errors as possible, like in this format and so on. So finally, like I really wish to explore this direction about prompting like some super large model to introduce realistic errors of similar formats, but I can't do that due to GPU resource limits. But you're more than welcome to try it and let me know if it works. To conclude here, that is, I told you that in result 1, that is, language models actually often knows they have made mistakes, and its internal states can appear very regretful, so they really want to backspace, but they couldn't. If you allow it to backspace and to retry with randomness, then this is not very efficient, both in terms of time efficiency and also the accuracy improvement and so on. So therefore, the majority of this paper is actually testing a different idea, that is to pre-train a model with error followed by their immediate corrections, and we noticed that this can give you a much higher accuracy boost, and in fact also the more errors the better. The models can just learn to correct errors on the fly. There's no multi-stage prompting and so on. So that's a very nice type of data that if you can add, that would be best. And we also showed you some negative results, namely like if you do beam search or fine-tuning, especially lower fine-tuning, then you don't get this much of accuracy gain. So therefore, like to make the model really be able to correct errors, you really want to introduce such kind of data at the pre-training stage. And finally, like I showed you some preliminary progress towards maybe how to prepare some fake mistakes. And we noticed that at least our synthetic data, generating such fake mistake is almost for free. You don't need to understand the problem, just randomly shuffle like the solution steps, and still like you can get some very high accuracy boost and so on. So I would just end here and thank my wonderful co-authors. So Tian Ye is a grad student from CMU, also my intern. Zicheng Xu is my colleague at Meta. And Yuan Li is a professor from MBZ UAI, and this is me. Thank you so much for your attention. So see you next time.